So welcome again, Kimura. We are really looking forward to listen to your contribution to the same topic. And you're welcome to start sharing the screen. And while you do that, I quickly want to remind the participants to please stay with us after this talk, because we want to take again a group photo, because today we have some participants that were not there yesterday. Yeah, and we would like to include them in the group photo as well. Thank you very much. Again, please, you're more than welcome to start with your presentation. Thank you.
Thank you very much. Do you see my slide?
Yes, perfectly. Thank you very much.
Okay. So first of all, I'd like to thank all the organizers for giving me a chance to speak at this very important workshop. It's a great honor indeed to be here to celebrate one of the greatest kind of hidden milestone by Professors Sudarshan, Matthews, and Rao. This is also another picture which Derek has shown from Toron Symposium in 2016, which I love very much. Because look, everybody is smiling at great physicists, especially Professor Sudarshan and Professor Kosakowski, my mentor. So it's a great pity that we cannot meet them any longer, but I do believe that they are seeing us smiling from the heaven. So my talk is a continuation of Derek's. While his talk mainly focused on our conjecture, in my talk, I would like to stick to the universality of the constraints, reflecting the complete positive condition. In particular, we introduce a strange functional, which we called an R function. And by analyzing the upper bound, we get a universal constraint for relaxation rate, which are satisfied by all completely positive Markovian dynamics, namely by all GKLS master equation. Now, this talk is mainly based on the two joint works with Derek and Professor Ono, as well as my students Ajisaka, Watanabe, Fuji. Although Derek has already beautifully explained our motivation and goal, let me briefly re-explain them slightly in a different perspective. Indeed, our study is motivated by a very simple question: why we need completely positive condition. From the beginning, I learned about the Shippy condition. Indeed, for about 20 years, I have asked myself why this condition is universally required. On the one hand, it is true that your system of interest is and generally must be a part of a composite system with an ancillary or an environment, so that the time evolution map, should preserve positivity not only for your local system, but also for the total system. And this almost brings you the complete positive condition directory. But I feel like this argument is a bit artificial. For instance, why we require the positivity condition for an arbitrary ancillary, not only for a particular ancillary. On the other hand, the standard reduced dynamics can be used to prove the Shippy condition directly. Indeed, if the total system is isolated, so it's governed by a unitary dynamics according to quantum mechanics, then taking the partial trace over the environment, the time evolution map for your system is proven to be completely positive. However, provided that there are no initial correlations. So one can naturally ask, what happens if there are initial correlations between your system and environment? And of course, there is no guarantee that quantum mechanics will ever be correct. So what happens if we consider a new physics? So I still believe that I believe it still deserves to ask whether completely positive condition is always satisfied or not. Sorry. I indeed know that I am overreaching myself to ask this sort of adventurous question. I am quite encouraged by this word that Professor Pascaccio introduced yesterday. Professor Sudarshan would never take a postulate for granted. Okay. Indeed, according to the very discipline of natural science, the validity of a theory should be ultimately determined by experiment. So what we need is to understand the physics of complete positive condition. More precisely, by assuming completely positive condition as well as other conditions if necessary, we want to have some necessary condition which is testable by experiments directly. One may compare this with the famous Bell's theorem. By assuming essentially reality and locality, Bell obtained the famous inequality, and importantly, this inequality holds universally for all local realistic models, independent of the underlying model. And moreover, the inequality is written in terms of the measurable quantities. So this can be directly verified by experiment. In our case, we assume completely positive condition as well as the Markovian assumption this time, and are looking for the experimentally testable necessary condition. And namely, we like to analyze quantum dynamical semigroup or GKLS master equations from a general point of view. As Derek explained, our necessary condition will have this form where our measurable quantity is relaxation rate. Okay. Luckily enough, we have a nice representation theorem by Golini, Kosakowski, Sudarshan, of course, and Lindblad for a general quantum dynamical semigroup, which essentially assumes complete positive condition and Markovian assumptions. The generator has a Hamiltonian part where H is a self-adjoint effective Hamiltonian, and dissipative part looks like this. Here you have the positive parameters and jump operators, but in the following, let me incorporate these parameters into the jump operators and rewriting this equation like this and omit this tilde. So this is slightly different from the direct notation. Okay. And in this work, we restrict ourselves to a D-level quantum system where small d is the associated Hilbert space dimension. But please notice that although it is finite, you can choose any finite d arbitrarily. Okay. So to understand the physics of the GKLS master equations, we focus on relaxation types. Because any time evolution of any physical quantities is a superposition of this kind of exponential decay multiplied by the polynomial time function at the most. And the decaying time is determined by the eigenvalue of the generators, and the relaxation rate is defined by the minus real part of the eigenvalues. And the inverse is called relaxation types. Let us re-emphasize that different from the just a parameter appeared in the GKLS generators, the genuine physical quantities directly testable by experiment is this relaxation rate or relaxation time. And there is always a leading eigenvalue 0 due to the trace preserving properties. There are generally d square minus 1 numbers of relaxation rates. So here are our main results. We have shown that for any d-level GKLS master equations, any single relaxation rate cannot be too large and is bounded from above by these quantities. And notice that this includes only the measurable quantities, and because GKLS master equations assumes essentially only complete positivity condition and Markovianity, we believe that this kind of inequality will serve as a necessary condition to check the CP condition and Markovianity, which is testable by experiments. Namely, if you ever find an experiment which violates this inequality, you can immediately judge that your experiments can never be explainable by GKLS master equation. And this is indeed derived in 2017 by us, and quite recently we succeeded to sharpen this bound to this and also to this. So using the rest of the time, let me briefly explain our idea. And indeed, this proof is based on by introducing the so-called R function, which you will see the definition soon. Okay. Here, this is the definition of R function. For complex matrix A and B, we define the relaxation functions by this quantity. By using the cyclic property of the trace, you can rewrite this definition slightly in an elegant manner, where these brackets commutator and anti-commutator, whereas this bracket denotes the Hilbert-Schmidt inner product. And the operator norm for my talk is always Frobenius norm or Hilbert-Schmidt norm. And we'll see soon that by using R functions, relaxation rate can be beautifully expressed. So that's why we called this R function, where R stands for relaxation. Some properties of R function. You can easily prove that it satisfies the unitary invariance and quadratic nature. And what was good for us, technically, is that for Cartesian decomposition of operator, the relaxation function also can be decomposed like this. So let me start from some lemmas. the sum of all the relaxation rate can be written by using the norm of the jump operators. Oh, sorry, I forgot to tell you. Yeah, sorry. Without loss of generality, we can always assume that the trace of the jump operator is 0. If not, you can renormalize the term into the Hamiltonian part. So in the following, we assume the traceless condition for the jump operator. Okay. This is proved as follows. Firstly, the sum of all the relaxation rate can be written by summing all the eigenvalues of the generator with minus sign. Therefore, it is minus trace of the generator. This is because the complex eigenvalues of the generator appears always as conjugate pair, so that if you sum eigenvalues, then the imaginary part disappears. And also you can add the leading eigenvalue 0. And also, there is a nice expression of the trace of the generators to the best of our knowledge, which was firstly pointed out by Wolf and Sirac, like this. But their proof was somehow tricky. So let me introduce a much more simpler proof by using the tensor representations actually related to the Sudarshan's representation that was beautifully explained by Professor Lakshminarayan talk yesterday. The generator can be written in this tensor product form. So by taking the trace, this term disappears, and remembering that we are assuming traceless condition for generator, this term disappears, and this will bring you this expression. Next result is the origin of the relaxation function, the name of the relaxation function. Any single relaxation rate can be written by using relaxation function, applying it to corresponding eigen matrix and jump operator. The proof is very simple. Starting from the eigenvalue equations and using the GKLS representation, multiplying the U alpha dagger and taking the trace, and finally taking minus real part of the equations, you will immediately get the relaxation rate is expressed by these equations. But here is the definition of relaxation function for eigenmatrix and generators. So this is only the reason why we call this function R function, where R stands for relaxation. The key proposition for our main result is as following. If you ever find an upper bound of the relaxation function in this form, then you can show that for any GKLS master equations, relaxation rate satisfies this constraint. So you get the universally valid constraint by analyzing the upper bound of this strange R function. The proof is based on lemma 1 and 2. Starting from lemma 2, by expressing the relaxation rate with respect to R function and applying this upper bound, a null of U alpha cancels and CD go outside the summation, and using lemma 1, where this sum of the norm can be written by the sum of the relaxation rate. We get this universal constraint. Our first result is the following upper bound of relaxation function. The relaxation function is upper bounded by square root of 2 multiplied the square of a norm of A and B. The proof goes as follows. Starting from this expression for relaxation rate, by using triangles and Shibaura's and norm inequalities, we have this one. And finally, by applying the Böttcher-Wenzel inequality, this one, which actually directs also used in the previous talk, we get this inequality. So with this upper bound, applying to proposition 3, we get universal relaxation constraint. Actually, this was indeed derived slightly in a different way in 2017 by ourselves, but we have new proof to derive the same result. But with this R function approach, of course, what is good is to find the best constant, CD, such that the inequality is saturated by some matrix A and B. In other words, we need to solve this kind of optimization problem. And we indeed succeeded to solve it. The result is that R function is tightly bounded by these quantities. I don't have much time to explain the proof, but let me briefly explain the idea. By using the unitary invariance and the Cartesian decomposition for R function, one can restrict the matrix A to be diagonal like this. Then we can obtain the R function with this like this, and by using this constant, we can complete the square. So this we prove this inequality. And similar, by using this, achievability is also easily shown. So because of this optimization, using proposition 3, we get tighter universally valid constraint like this. Okay. So one may anticipate that this bound then can no more be improved by using R function approach, because we have actually used the optimized upper bounded. But because we apply R function for eigenmatrix and jump operators, we can somehow use some property for eigenmatrix or generators, or maybe the relation between them. And indeed, it is easy to show that eigenvector or eigenmatrix belonging to non-zero eigenvalue is traceless. This is due to trace preserving property. Therefore, we can restrict the traceless matrix A for obtaining the best constant. And similarly, we have succeeded to obtain the best constant, which is this one. So applying proposition 3, we get the tightest constraint for GKLS master equation. And interestingly, when D is 2, then this recover my old relaxation constraint, which is in the tightest one. So let me conclude. Based on R function approach, we have found universal constraint for relaxation rate, this one. And we believe that these conditions will serve as a necessary condition to check the complete positivity and Markovianity, which is most importantly testable by experiments. But as Derek explained, we believe that the tightest constraint will be this one. But unfortunately, this is still conjecture. We welcome your comments and idea, and actually your participants to complete this project. So thank you for your kind attention.
Thank you very much, Professor Kimura, for sharing these very impressive results. And I think you are close to show us the proof of the last conjecture. Yeah. So thank you very much for that. That was really very nice. Yeah. Are there questions for Professor Kimura? Ah, yes, Usha, please. You have to, yeah, you already unmuted yourself, please.
Thank you. Very nice presentation. I got just curious that anytime when we write a Markovian Lindblad equation, we have varieties of Poissonian process or a diffusion process. Both would lead to the same kind of a master equation, basically. So these relaxation rates seem to be independent of the undergoing Poissonian process, jump process, or a kind of diffusion process. Have you thought about it? Do you have any comments on that?
So
I
sorry,
hope my
maybe
question is clear.
I don't understand what is Poissonian.
All right. Okay. So in quantum stochastic dynamics, where we have a stochastic Schrodinger equation, and I average over all the noises, that is, say, Poissonian or diffusion kind of thing, I would get the same Lindblad master equation. So in that sense, it was curious that these relaxation rates, basically the kind of conditions that you show, it seems that it is independent of the trajectory approach. It's overall, it seems to obey this kind of inequality. So that's what made me ask you this question. That is, underlying trajectories leading to master equation. There can be different kinds of trajectories. One is diffusion, other one is jump, but both will lead to same kind of equation. So I just wondered, there could be some differences in the relaxation rates there. But no, it doesn't appear to have such a difference.
Okay, thank you very much. Actually, I have never thought about like that way. But of course, after you get the GKLS generators, then relaxation rate is automatically determined. But of course, it should be dependent on such kind of trajectory and so on. So maybe it would be very interesting question.
Yeah, thank you. Thank you.
Thank you, Usha, for the nice question. Are there further questions or comments to the talk? I don't know if Darius would like to comment since he's also involved.
No further comments at the moment. We still, working on the proof. So if the proof is ready, we would be happy to announce it.
But I think it looks like you're very close. Yeah, you're getting closer and closer. Yeah, so just a small step. Yeah, excellent. Then Professor Kimura, thank you so much. It was really a very interesting update on the fruits of your work. So there is some merit in focusing on a very well-defined question for some time, and the progress is really impressive. Thank you very much.
Thank you very much.
Thank you.